So I will talk a bit about something that has been mentioned in the two talks before me already, the relation of thermodynamics, or in general physics, of formalized approaches to life, and of course the famous What is Life book or lecture series by Erwin Schrödinger. My focus here is on the concept of non-equilibrium steady states. I will explain what that is and how it relates to minimal models of life. This is where the Loch NESS comes from, because NESS is the famous abbreviation of non-equilibrium steady states that's been flying around in all the free energy papers, where they just use a lot of abbreviations, which makes it from coming from outside of the field very hard to follow their argumentation sometimes. That's why I kind of called it the monster of Loch Ness. Then I will talk about the direct application of free energy and life. The Friston and free energy principle people are not the first ones who thought about how to apply free energy to life, but they're definitely the ones that are heavily debated at the moment. And since we already had this nice talk about boundaries, talk about the famous boundary of the free energy principle people, the Markov blankets. And from this, they derived a kind of philosophical foundation called Markovian monism. I will present them to you and give a little bit of an analysis of how it maps to approaches in cognition and life, and the problems I see with it, and some ideas I developed in the last months to maybe strengthen the Markovian monism or change it in a way to make it more compatible with other current approaches to life. So let's start with the one and only question: what is life? Obviously, Schrödinger was not the first one who asked that, but definitely influential in providing a physicist's perspective on a question in biology, together with the period where the development of molecular biology was very promising. There was kind of this hope that physics will live up to the promise of unifying all mechanistic theories and having to say something about life. Obviously, the lecture and the book itself inspired a lot of research, but all of these concepts are used in a different way now. So something that has been called Schrödinger's paradox was how living systems can resist the second law of thermodynamics, which basically says that entropy increases, so the number of possible states a system can be in increases over time. And paradox, something I actually wanted to put in quotation marks, because the only thing that the second law of thermodynamics says is that entropy increases for closed systems, which are independent from the environment. And as we all know, living on a planet in a big universe with getting energy from the sun and exchanging heat with the solar system, we are in an open system, and all living systems only can maintain their dynamics in an open system in interaction with its environment. It doesn't make sense to think of living systems as closed systems, because they would be thermodynamically dead. So I want to kind of reframe Schrödinger's question in the way that Lynn Margulis posed it in a recent introduction of a new edition of Schrödinger's What is Life, where she says, how can the events within the spatial boundary of a living system be described by physics? And this is obviously an open question. We don't know if physics can give sufficient criteria how living dynamics work, but it's definitely an interesting avenue to investigate. Another thing that is very influential, we also saw Watson and Crick before, and Rosalind Franklin, they all said that they're inspired by Schrödinger's idea of genetic information being stored in an aperiodic crystal. Crystal is the simplest self-organizing structure you can have, a static self-organizing structure, and aperiodic because it has to encode different states of information, which in a completely homogeneous crystal, you cannot encode information because it's perfectly periodical. So here's a little zoo of animals feeding on free energy. What that means, I will tell you in a second. I just need to keep the time because I'm really looking forward to your questions. I don't want to stretch my 30 minutes too much. So I have this beautiful TikTok video for you, but I just have the PDF now, so I'll explain what it means. I will reenact it. Ella said she wants to reenact it. So first of all, now these minimal models of life, they start with the idea of a non-equilibrium steady state. So a steady state in a thermodynamic sense is an equilibrium that is used to take a very complex system, for example, billions of gaseous particles in a room, and describe it with a simple average variable. So you have a lot of microscopic dynamics, how every particle moves in a gas, and you try to get an average description like a macroscopic variable. For example, you have temperature as a description of an average of the molecular velocities of all the particles together. Obviously, this description, this macroscopic variable only makes sense if they're in equilibrium, so you can assume that they have roughly the same dynamics, they are roughly in the same state. If you have a very turbulent flow, like a lot of different areas of temperature of gas, then an overall temperature doesn't tell you much about the behavior of the system anymore. But such a thermodynamic equilibrium is not something that biological systems can sustain in for a very long time, because all biological processes, from metabolism to reproduction to perception, they all depend on exchange and transport of different particles, and this is not possible in a thermodynamic equilibrium. There's basically no exchange anymore because everything is in the same temperature. So a nice concept here that builds on this is the non-equilibrium steady state, the NESS, which is stable in the sense that there is a certain kind of structure that is maintained over time. There is a certain kind of process that is there and continuously fueled by some external energy. So, for example, water vortex is a simple non-equilibrium steady state that you can think about. If you have a glass of water and a little turbulence going on, by some external energy you give to the system, you can create a kind of vortex that is there. Obviously, the vortex itself, the particles are moving all the time and the particles exchange, so it's not static in any sense, but still the process is continuously there. And in this video from TikTok, you have this nice example of water vortex where there was going around like a couple of months ago, where people put 2 batteries on a glass of water and then a vortex magically appears. So this is kind of the idea that the batteries input some energy into the system to create this water vortex. Obviously, as everything on TikTok, it was fake because people just make a little vortex and then put the batteries there and then reverse the video. But yeah, this is like scientific explanations on TikTok, I guess. Still, if you have like a flow in a river or something, you have a lot of energy that goes into like keeping up the turbulences in local areas of the river. So just think of it as a process that is continuous, but it needs energy to be sustained. Okay, so how does the free energy principle use that now to explain the origins of life? So the free energy principle in general is an idea, a model of cognition that has been applied mostly to brain function, to perception and action, how we make sense of the world. And this idea has been described as a principle of cognitive self-organization. So like making sense of the world is a fundamental self-organizing process, because if I can create a model on the world that I can act on in a way that my boundaries are stable, that I don't diffuse into the environment. If I don't have any idea what's going on beyond my boundary, I don't have any way to react to it. For example, to temperature changes or other threats that could be there. So the free energy principle, just in a nutshell, I'm not going to go into the mathematical details, but it's a mathematical framework inspired by statistical physics and machine learning. And in a nutshell, you can say the free energy principle says that cognitive agents aim to minimize surprise about environmental states. This basically means that if we make our environment predictable, we can survive in it. So predicting the environment is key for survival, that they say. Links directly to a lot of other organizational principles that we talked about before in biology and in neuroscience, like autopoiesis, the act of self-production, the maintaining of boundary in the world, and homeostasis, the concept that biological system can maintain a set of favorable states. For example, you can think of body temperature as an homeostatic process, because you only have a very limited range of body temperature states that you could actually maintain biological functioning. If it goes below 36 degrees or above 39 degrees, you cannot maintain biological function for a very long time. So it's important to self-regulate in a way that you're in this homeostatic range. And the boundary explanation in the free energy principle comes from this notion of Markov blanket, which is inspired by probability theory, where you look at statistical dependencies of internal and external states. So a Markov blanket is what separates the internal states in an organism from the environmental states, the external states. And this is a separation that basically consists of two parts. So the Markov blanket state has a sensory part, which is kind of the sensory information that the organism gets to predict the environment, and the active states, which are the actions that the organism can take to change environmental states in accordance with predictions. So you not only get passive information, you don't only compute what's out there to make sense of the world, but you actively sample the environment in a way that is in accordance with your model. So this is definitely, it's neither bottom up nor top down, it's kind of like the interface is exactly in the middle between top down predictions and bottom up information coming in. That's the link to the predictive processing framework, if you ever heard about that in cognitive science, where cognition is kind of explained as prediction error minimization, and mathematically the free energy principle and predictive processing are equivalent. Okay, I already talked about homeostasis. So the question is, how does non-equilibrium steady states now relate to homeostasis or other organizational principles that we know from biology? And the idea here is that homeostasis, according to the free energy principle, is achieved when internal processes predict the environment good enough to maintain a Markov blanket. So this modeling is something very pragmatic. It's not about getting a good representation of what's going on in the environment. It's about getting a model that is complex enough that we can act on the environment in a predictable, interesting way, but not too complex, because there is no point in having a very detailed model which costs a lot of energy to maintain. So, according to a recent paper by Chris Fields and Michael Levin, free energy minimization directly leads to attractive states. So, like, minimizing free energy always, according to the argumentation, leads an organism to stay close to a non-equilibrium steady state. So this non-equilibrium steady state is like something that makes it possible to uphold the eigenbehavior, or like the stable behavior that the organism needs to maintain itself, even though the environment is dynamic and constantly changing, and it's not about keeping the particles the same, but keeping the organizational function the same. Okay, so this applied to a simple organism would mean that we have some organism that has some internal states that are there to track what's going on in the environment. And this it does by sensory states and active states. And in this kind of formulation that they put forward recently, the environment is not something static, not something reductionist in like a thermodynamic sense, where you would say, okay, the environment in a thermodynamic sense, usually it's just assumed there is a heat bath. Heat bath means there is an infinite reservoir of energy with a certain temperature. So in their sense, the environment itself is an agent. And relating this directly to other origin of life models, the Fields and Ledden paper says, the environment similarly provides both parts and stabilized microenvironment in origin of life models. The free energy principle suggests that it does this for the same reason that it does this in the case of DNA replication or organismal reproduction, to increase its future predictive power. So I think the framing here is very interesting because they actually turn the whole thing around. It's not about the organism predicting the environment, but it's about the environment increasing predictive power about the organism. So you can already see that internal and external is kind of a mirror image, and it seems like a kind of arbitrary to me in the way they talk about it in these recent papers. So the Markov blanket as a boundary is actually more important as a separation, and not as much as important to like delineate what is internal and what is external. It's more like a difference maker. So the boundary allows internal states to model external dynamics, but if we follow the quote, it also goes the other way around, that it allows external states to model internal states. So our intuitive notion of scientific modeling is not the thing that they talk about when they talk about modeling here. And generally, you can boil it down to saying that better models of environments or of agents help you to be better at self-organization and maintaining homeostatic states. They call this self-evidencing as sentience as like high-level form of self-organization. You have a model of the environment, but if you also have a model of yourself in this environment, this is, according to them, this is sufficient to have sentience. It's a completely different discussion. If that is sufficient, I would agree it's necessary, but definitely not sufficient to get something like subjective experience or phenomenological qualities, but they are not there yet. So what are the philosophical commitments that follow from this perspective? So according to, I did a bit of like literature review, and I tried to identify what is the free energy principle. And because it's described in a lot of different ways, it's applied to cognitive systems, to living systems, to sociological systems, to the brain, to artificial neural networks. It's applied to a lot of things. So from scanning the literature, the free energy principle is a grand unifying theory, a modeling framework, a modeling heuristic, which is a bit weaker, a new branch of physics, they call it the physics of beliefs, a formal ontology with all the commitments that they make on what their models entail, and following a nice philosophical analysis by Mel Andrews, the most useful description is the free energy principle is a model structure without any empirical content. She formulated that in a very critical way, but my reading of that is being a model structure without empirical content is not something bad, but something like a general tool that combines a lot of different approaches that have been there before. We have autobasis, we have homeostasis, we have predictive processing. It also connects to Bayesian brain ideas. So a model structure in the sense of Andrews is a concept that with a lot of other hypotheses, can be made into a concrete model which can be applied to describe the brain, describe self-organization of biological systems. It doesn't mean there is one model for everything, like a grand unifying theory would imply, but there is a shared structure in which people put empirical facts and other hypotheses in to get a specific model for a specific phenomenon. So yeah, I made this little meme to summarize my literature review. Carl Friston, the inventor of the theory, applies this kind of principle to like a lot of different systems. During the pandemic, he tried to model pandemic evolution with the free energy principle. At least that's what he said in interviews, and then like he never followed up on it, so I guess it was not very useful. So he kind of sees it as this grand unifying theory, and a lot of philosophical debate more focuses on that it's like they're not good at explaining their mathematical argument to a wider audience. So there is a lot of articles saying, yeah, this is all confusing. But according to my status right now, I think it's like a consistent mathematical framework, and how we apply this mathematical framework to cognition and life, that is up to specific models. And this is the interesting route to investigate the free energy principle. Okay, together with philosopher of mind Vanja Wiese, Carl Friston wrote a paper about the philosophical foundations of the free energy principle and the application of Markov blankets to living cognitive systems, and they came up with the following definition of their philosophical perspective, which they call Markovian monism. So Markovian because we're talking about Markov blankets, and monism because they reject dualistic or reductionist perspectives. So according to their paper, the main components are: one, there is only one type of thing and only one type of irreducible property. That one type of thing is Markov blanket. And second, if systems have mental properties, then they have them partly by possessing a Markov blanket. So basically, the separation of internal and external, the act of separating the object that does separating the Markov blanket, is the fundamental process in their view. Which I think intuitively, I like that, but I'm still confused about the formulation. They have mental properties partly by possessing a Markov blanket. This kind of leaves open, like, if there is only one thing, why does it not sufficiently explain mental properties? Is there another thing, or where does the partly come from? This is something they have been asked a lot recently, but have not formulated an answer to that yet. So what they clearly stated is they accept the kind of mechanistic philosophy, they accept physicalism in a very instrumentalist way, and some modest representationalism. So their models represent something about the environment, but representation is not in a strict ontological sense. They reject the dualism by saying that Markov blankets is all there is. They also reject that their physics of belief is a way of reducing cognitive actions to physics. They kind of say it's a new type of physics, a new set of laws that are not derivable from physics itself. And they also reject epiphenomenalism. So the idea that mental properties or living properties are something that is kind of on top of biological dynamics but doesn't have any causal role. So they say there is a causal role of life and cognition on the microphenomena going on with it. So this is kind of an interesting perspective, including a lot of different debates that have been going around in the models of consciousness debates about how how to model consciousness. And according to like what I heard from you so far, these debates highly overlap with explanations of life. And this kind of reasoning that this free energy principle, the minimization of free energy, is sufficient to describe living processes, is something that Maxwell Ramstad, one of the main drivers of the field at the moment, called a strange inversion of reasoning. I will first give you the quote and then explain what that is. So Maxwell Ramstad, in a paper from this year, says, the resulting philosophical perspective is not physicalist reductionism, a reduction of causal efficacy to mere physics, but rather a deep commitment to anti-reductionism. Unfortunately, in the paper, this is the only sentence he says about that, and I think there's a lot of things to unpack here, which I'm still trying to do. But I think it makes a lot of sense to think about with this concept from Daniel Dennett, with the strange inversion of reasoning, where it's not about giving a principle from which you can derive that systems are alive, but the other way around, to first look at living systems and then try to model them with the tools you have available. So basically to say, organisms must not minimize free energy to exist or to survive, but if they exist, they can be modeled as minimizing free energy. This is an interesting perspective that comes out of the Melendrus paper that I showed you before. She's a philosopher of science who kind of like critically analyzed all their ontological commitments, and they read it, they replied to it, and there was a very interesting debate. And she basically gave them the argument that this is not one model that can be applied to anything, to everything in the same way, but there are a lot of commitments that they make depending on which phenomenon they look at. And the thing that changed after this debate was that they don't say anymore that the free energy principle models living systems, but now they say living systems can be modeled as minimizing free energy. So it's kind of like a reframing, but it doesn't change their application in any way. Coming to the discussion also we had before about constraints and boundaries, I think to me it makes the most sense to understand this as the free energy principle showing that there is an emergence through constraints. So constraining physical dynamics enables self-organization and not having a new set of laws that are independent from physics. I kind of like polarizingly framed it as the whole is less than the sum of its part. Think about like an engine. An engine can only drive a car because its motion is constrained in certain degrees of freedom. If the piston of an engine could go in any direction, there would not be any work that could drive the car. So constraining a system can actually lead to self-organization. I always wanted to call this demergence because like I've never heard that term before. I want to write a paper one day, just call it demergence. So how can we get out of this mess? I don't know if I can contribute to it, but my perspective on this is something. So the free energy principle people and the inactivists now started the big fight. Thompson and Di Paolo wrote the paper how these approaches are not compatible with each other. And the free energy principle people didn't like that because some of their papers are really overlapping. But I still think they can be combined, not in the state that they are right now, but if we take a non-representational perspective on the free energy principle, I think it could be a very fruitful modeling strategy for embodied systems. So, to take a non-representational perspective, I would say it would be important to take the internal-external distinction as the most important part. So sense-making is about differentiating between internal and external. It's not that internal and external are pre-given, but like making these distinctions is what enables self-organization. So this can only be done in relation to the boundary dynamics. Yeah, again, I should also say the boundary, because we talked about it, it's not a material boundary in the sense, of course you can think about like the boundary of a cell as something material, but in their discussion, the Markov boundary is an informational boundary, which separates statistical dependencies. So it's about the flow of information. You could say it's a relational boundary or an interaction boundary, and not a material one or a pre-given one. The process of separation is more important than the distinction itself. You can see that by it's easy to flip the labels between internal and external. So it's more about like where do you draw the boundary and not what is inside, what is outside. I argue that the Markov blankets that they talk about are more of a dynamic coupling instead of a closed thing that represents external states. And I discussed this with Maxwell Ramstead already. It would be interesting to go back to the idea of formalizing or naturalizing phenomenology instead of discussing contemporary theories of nectivism. So like going back to Varela's ideas of formalizing phenomenology could be something where the free energy principle could have something to say about it. And to give you a little bit of an idea of how easy it is to switch the labels between environment and system, between internal and external, and also to give you a bit of a taste how fun it is to read these papers. The Fields 11 paper says the environment of any system shares a Markov blanket with that system. The environment E of any system S is therefore a free energy minimizing agent. VFE stands for variation of free energy. I'm not going into the distinction now. To assume that environment's generative model is random, that E functions only as a resource, is thus to assume a very special case, one that is largely irrelevant to biology. So here they say explicitly that like regarding the environment as something static, like a heat bath and thermodynamics, is something that is irrelevant to biology, because if you take an agent perspective on the environment, then you talk about environments that are more biologically plausible, because biological agents usually interact with each other, are in a symbiotic exchange, so what the environment does should also be described as from an agent perspective, and not as something static like you would have in thermodynamics. And this is basically the closing of the argument why non-equilibrium steady states are important, because thermodynamic equilibria are not very interesting to describe biological dynamics. So that's my conclusion. I think we have 10 minutes for discussion. So I'm just going to wrap it up real quickly. So the non-equilibrium steady states, I just argued, are useful as a modeling tool for living systems to constrain or give necessary conditions, something that has been called minimal models of life. What are the necessary conditions for life, and not what is a sufficient physics perspective. Following Wimsatt, I would say that we're limited beings with limited epistemic access, and this is something that can be seen in a free energy formalism, but is it really sufficient to describe living beings as free energy minimizing systems? I try to argue why I don't think it's sufficient as it is right now. Something I stole from the paper titled by Sanchez and Canizares is a nice conclusion of the state of the free energy principle right now. They say, the free energy principle, good science and questionable philosophy in a grand unifying theory. I think if we drop the idea of the free energy principle as a grand unifying theory and look at more at how it's a shared modeling approach, we also could have more interesting philosophical discussions with it. There, of course, you have the problem with like they say that then just, yeah, it's instrumentalistic perspective. We just model something with Markovian monism, but philosophically and what it says about the commitments of life models, instrumentalism is not very interesting. I gave you a bit of the ideas that I had about like including a non-representational perspective there to fix this circularity of free energy agents and its connection to life. So being a free energy minimizing agent, is that sufficient to be alive? No, because they do it the other way around. They look at living agents and then say, or model them as they're minimizing free energy. I think by taking, like, going back to Varela, we could definitely benefit in the philosophical discussion. So these are my references and like a nice picture of our group. Yeah, you can see Gregor up there. Yogi, who will not be here tomorrow, unfortunately, but over Zoom, yeah. He speaks over Zoom, is sitting there, and yeah, this is our webpage. Thank you for your attention.
Just like to add that Andrea and Tarja originally were also supposed to be.
Yeah, right. So yeah, Tarja, our PI here, and Andrea was not there.
Yeah. Okay, we have time for approximately 2 questions, and then we have another short break, and then we have a discussion. So after the short break, I would just kindly ask also the speakers just to find their seat, wherever they want, near a mic, the closest mic. So, any questions?
Yes.
Okay.
Yeah, so I guess I can at least like coarse-grainedly understand like the connection between, let's say, like how this this would be a unifying theory of life and of cognition, right? So like there's a connection there, but then and you also said that like you think that this would be a more like productive thing to like specifically model living things and not like and you're as I understand, you're not really inclined to treat this as a kind of unifying ontology of everything, as Kristen does, right?
Yeah.
But then my question is like, what? So if you could explain me what Kristen means by this, like, I've heard him say somewhere that like he understands everything in existence insofar as it exists at all, is insofar as an object has to be a free energy minimizing system.
Yeah.
So in this sense, like, first of all, I really don't quite understand what, like, how, in what sense that does any system like actively minimize, if that's even like a relevant distinction here.
Yeah.
And then what precisely would you say that such a theory would actually say something specific about life, if this is indeed like something that could be equally applied to any sort of, let's say, stable phenomena, like stable object?
Yeah, that's a very good question, which I won't be able to give an answer, because I've been looking at that for some time, and the big distinction that I could make out so far is that like you have the free energy principle as like a fundamental principle how systems evolve, which doesn't make a difference between like physical systems, living systems, cognitive systems. It assumes that all these systems evolve according to the free energy principle. But then you have active inference as a process theory of how you can minimize free energy through action. And that is something that physical systems cannot do, or only can do on a very basic level. So you can think about a crystal as like a very simple self-organizing system in the way that like it maintains and reproduces its own structure. But it's not something that it can like actively use to act on the world. So like sampling environmental states is something that living systems can do, which physical systems cannot. So the free energy principle in one paper is also applied to stones, and stones clearly don't act on the environment in a way that would sample it. Like stones exist because they have a certain kind of stable structure, according to the free energy principle, but it's not something where they have sensory perception or action on the world. So it's true, like some of the parts that I presented apply more to active inference as like the process theory derived from the principle itself.
Just a quick sub question.
Yeah, please.
The stones, if I understand them correctly, you could say that the stones do represent the environment, right?
Yeah.
Yeah.
Yeah, sure, because like the structure is based on the wind coming in and like the temperature they're in. So there is a dynamic coupling, but it's not sensory information gathering or active sampling of the environment. I don't know who's first.
When you talk, the difference between so the heat bath environment and like why we should actually think of the environment more as the environment of the organism, and also this like this loop that Levin and the other fields.
Yeah.
So in general, you would agree with like this. That's one question, and the second is when you talk about so the world of an organism, is it connected to this like Varela said that like by maintaining an identity you get like like a springs forth a world of the organism, right?
Yeah.
So that's like a sphere of relevance that like opens up with the maintaining of identity. So is that the kind of like this world of organism that you contrast with a heat bath, or just like this, or is it a distinction on another level?
Yeah. So the question, I would like to start with the second one because I don't think I think the distinction is on the very same level. It's kind of like is the environment some kind of agent that provides some structure, or is it only a resource that provides energy? And like as a resource that provides energy, it's not acting, it's static. And if you look at it as an agent, it can provide like what they call like the micro environment for the biological organism to self-assemble. Because when we also talked before, like looking at the environment as like something stable, it still needs to provide like the parts for protein synthesis and like the right temperature and stuff like that. So I think you need to look at a more complex environment than thermodynamics does. I think that's the only argument so far.
Okay, yeah, because I think there's I mean, one thing is to talk about the environment as an agent, like what does that even mean, Like, okay, the environment is structured, okay, and it's structured somehow, but this world of the organism is not like, does not capture like the structure of the environment as is, for instance. Like for instance, the classic Wake School tick example, right?
Mm-hmm.
The tick does, its world is like comprised of like very specific parts of the environment, not of like the whole structure of it.
Yeah.
So in that way, there might be like two levels of this environmental structure. One is like the actual structure of environment, which is more complex than like thermodynamics, and the other is the world of the organism, in which
like the life world.
What is relevant is the world of the organism. Okay.
Mm-hmm. Yeah, when they talk about the environment, it's really about like the local environment and not making any assumptions about like the full picture of it all. And that's a bit why I tried to evade your first question of what if I believe that it makes sense to model the environment as an agent, if I understood that correctly. I think it makes more sense to look at it from a static perspective, but it does a lot of explanatory heavy lifting in their account of just saying like the environment is an agent. For example, in the paper they say, multicellular organisms are basically a way of the environment to be more predictable because like if you have multiple components that do the same thing, then it's very easy to predict them. If they all have the same processes, it makes a lot of sense. And like they use that for a lot of explanations, from like reproduction of species, of genetic variation. And so far from understanding their argument, I see how it helps, but I don't see how it's sufficient or like really justified to look at the environment as its own agent. Because they talk about it in a very teleological sense. And what is the goal of an environment? And I think that's kind of impossible to define.